DFT plus NEGF quantum transports calculations. So there is a device studio graphical user interface for modeling the nanomaterial, nano device and transistors applications. There is a simulator called NanoDCAL where you can add the buffer in your device structure in the left side and right side, virtual crystal approximation for doping and some create a compound device with dope N type or P type with the compositional concentration. SCF calculation for self-consistent field calculation to define the DFT parameter, key point sampling, relaxation to relax and optimize your device structure. You can relax using MD. Transistor option is there for 3-terminal device where you can define the gate and apply some different biasing on the gate terminal and plot IBDVD characteristics. And there is some analysis part where you can plot the material characteristics like density of state, effective potential, total energy, band structure, charge, SEN, phonon band structure, electron density, potential, transmission channel, eigenstate, full band structure, effective mass, complex band structure, ZT, phonon full band structure, phonon density of state, phonon transmission channel, modulus. And there is a device property called density of state, effective potential, total energy, scattering state, transmission coefficient, photocurrent, IB curve, charge, electron density, potential, conductance, thermoelectric current, Seebeck coefficient, and in many more properties also there which can calculate using this NanoDCAL tool. If you want to select it, you can select the transmission spectrum. The following parameter will generate. Transistors can also be plotted in this NanoDCAL tool. Hello everyone, in this video I will demonstrate you how to model the crystal using this device studio. So first of all I will go to the file option, then go to the import options. So either I can import the material from my material database from this import local online. So once I will click on there, this is material folders where a lot of materials are already exist in our database. If you have already HZW, XYZ or CIF crystallographic information, CIF file, postcard file, these file extension you can also directly upload in our device studio user interface. If the material is not available and you do not have any material file, then there is an option called import online where you can also search from the material projects open source library. Now I want to show you how to create the crystal from scratch. So I go to the file option and new option, then I click on crystal. The new crystal window will pop up where I can select my space group. There is 1p1, 2p1, 3p2, 4p21, 5c2. So these you can scroll down, you can find a lot of space groups are there. According to your convenience, you can type select the space group. Here this is called Brevis lattice. So accordingly the Brevis lattice will be selected. ABC, alpha, beta, gamma is there. According to your convenient need, you can choose the selected Brevis lattice parameters. So let's example, I want to define my ABC value. I have taken same value of ABC and alpha, beta, gamma, but you can take it different if you want. It's up to you. It's according to your convenience. Now I have to add the fractional coordinate of our element. So I want to create any NaCl structures. So I click on this plus sign and click on this add button and add the element. So I want to increase this window so that I can visualize it. Now I want to add another element. So I want to create the NaCl structure. So there will be 4 sodium and there will be 4 chloride. So I want to add 8 element. Now I have added this. Now I have to change the element. So I double click on this carbon atom and select the sodium from periodic table. Similarly, I will double click again on this carbon element and choose the sodium and select the OK button. Then again I follow the same procedure again and again and click OK. And then again I click on the sodium and select OK. Now this is my 4 sodium atom. And next one I want to change from this carbon to chlorine. So I will click on it and choose from periodic table and select the chlorine here so that it will become change. Because I want to create the NaCl, you can create according to your crystal build structure. I am taking as example here. Now I have selected all my NaCl structure. I have to define the fractional coordinate point. So let me define the coordinate point of each our element. So I'm putting these value. I click anywhere and then click on this preview button so that I can visualize my structure before it is final built it. So this preview is mainly to check whether the structure is correct. Now I can also, if you want, I can change this space group and accordingly I can define this various lattice parameter. Either I can take primitive cell or I can take conventional cells. So if I want to take conventional cells, I can click on it and click on the preview. And this is showing equivalent bond also. And then I can click on build button. Now your NaCl structure is ready. Modeling any other structure, just follow the same procedure. Click on file, new, and then click on crystal. The crystal builder will pop up, which will help you to create any kind of crystal material. For more information, please contact to Impulse Technology.
This is my device studio, that is a graphical user interface for this NanoDCAL software, and this interface will help you to model the structure. You can do some modification, manipulation in your atomic structure, device structure as well. So first I would like to import the graphene from my local database. So you can click on this file option, go to the import and select import local. And here you can see this is the material database that exists inside this software, where you can see 0D material, 1D material, 2D material, 3D material and some organic material is there. So for graphene you can select this 2D material, select this folder, and here you can see this is the graphene. Then you can select and click on this open file. So this is the graphene crystal structure that I have imported from my local database. So you can select this graphene, go to the mirror option, and here you can see this is the normal vector xyz. So I would like to select this xy, and here you can include the distance, and then you can copy this checkbox and then you can apply. So this is the double layer graphene structure, and then you can click on this center option so that all atom will be in the center position. So if you want to simulate this double layer graphene, so you can click on this simulator, go to the NanoDCAL, select this self consistent field calculation, and you can see this is the SCF calculation, where basic settings, electron temperature, cutoff energy, exchange correlation, LDA, GGA, and this is the K point sampling, this is the iteration control, density matrix, Hamilton matrix, total energy, and this is the basic settings, arrangement by element, by atoms, and this is the Howard atoms, and this is the Spintronics application. Suppose if you want to include collinear spin, general spin, So first I would like to calculate this double layer graphene structure without any gate pressure. So you can click on this generate file. And once you click on this generate file, in the project window you can see the scf.input file for this graphene double layer has been generated. So you can select this scf.input file, right click on open with, and this is the script for this double layer graphene structure. Here you can see what parameter we have defined. This is the basic settings. Here you can see no spin is included. This is the iteration control, and this is the atom and their Cartesian coordinate point. So you can select this scf.input file, right click, run option, and suppose if you want to run this job on parallel, suppose 5 core, 10 core, 15 core, so there is no limitation of core, you can define up to 128 core. Then you can click on this run option to run this job. In the job manager you can see the scf.input file is in the running condition. In the meantime you can select this simulator, go to the NanoDCAL, select this analysis, and here you can see this is the analysis parameter. So as per your need you can select the analysis parameter, and then you can click on this generate file. So I would like to select this band structure, and here you can see this is the symmetry K point, this is the Brillouin zone path, and then you can generate the file. So you can run the band structure.input file as well, right click, run option to run this job. So if you want to calculate the band energy for a double layer graphene under gate pressure, so you can copy the project. So you can right click on copy, and here you can rename the project, and then you can click on this OK. So you can select this project and go to the simulator, select this NanoDCAL, and here you can select the SCF calculation, and here you can define the same parameter as you have defined in this previous graphene, only you can define the gate voltage. So then you can click on this generate file, and once you click on this generate file, in the project window you can see the SCF input for this double layer graphene structure has been generated. So you can select this folder, right click on open with. So this is the script for this graphene structure, and if you want to include the gate voltage, so you can write this command, and in the object file you can enter the location of your previous project. So here you can see, so in the object file you can enter the location of this project. So you can copy this location, and here you can paste it, and then you can click on this save. So again you can select this scf.input file, right click, run option to run this job, and then again you can go to the simulator, select this NanoDCAL, go to the analysis parameter, and here you can select the band structure, and then you can click on this generate file. Similarly you can run the band structure.input file. So right click, select this run option to run this job. So if you want to define more gate voltage, so you can follow the same procedure. You can copy the project, and this time I want to include the 20 gate voltage. Then you can select this folder, go to the simulator, select this NanoDCAL, go to the self-consistent field calculation, and here you can define the SCF parameter. Then you can click on this generate file, and similarly you can select this scf.input file, right click on open with, and this is the script for this graphene structure. And if you want to include the gate voltage, so here you can write this command, and in the object file you can locate the location of your previous project, and then you can click on this save. Again you can select this scf.input file, right click, select this run option to run this job, and then go to the simulator, select this NanoDCAL, go to the analysis parameter, and here you can select the band structure, and then you can click on this generate file. So in the same way you can run the band structure.input file. You can wait until the calculation finished, and when the calculation finished, their output file will be generated in the project window. In the job manager you can see all the calculation finished and their output file has been generated. So this is the band structure.xml file without any gate voltage. So you can select this folder, right click on show view. So this is the band structure for this double layer graphene without any gate voltage. And here you can see this is the conduction band and this is the valence band. Again you can select this band structure.xml file, right click on show view. This is the band structure for the double layer graphene at 10 gate voltage, and here you can select this band structure.xml file, right click, select this show view, and this is the band structure for the double layer graphene at 20 gate voltage. So this is the band structure under gate voltage. So whenever you zoom at the highest symmetry K point, so here you can see I have zoomed the highest symmetry K point. So here you can see the band gap has been increased as the gate voltage increases. So first I would like to import the silicon material from my local database. So for this you can select this file option, go to the import option and select this import local. And here you can see this is the material database that exists inside this software. So for silicon you can click on this 3D material, select this semiconductor, and here you can select this silicon and then you can click on this open. So here you can see this is the silicon that I have imported from my local database. And if you want to simulate this silicon, so you can go to the simulator, select this NanoDCAL and select this self-consistent field calculation. So this is the self-consistent field calculation parameters. So here you can see this is the basic setting: electron temperature, cutoff energy, exchange correlation, LDA, GGA. This is the K-point sampling. This is the iteration control, density matrix, Hamilton matrix, total energy, and this is the basic settings. And this is the spin type, like collinear spin, general spin is there. So I am taking the default parameter and then I would like to click on generate file. So once you click on this generate file, in the project window you can see the SCF input for this silicon has been generated. So you can select this scf.input, right click and click on open with. And you can see this is the script that automatically generated once you click on this generate file. Here you can see what parameter we have defined. This is the basic setting: electron temperature, cutoff energy, exchange correlation, and here you can see no spin is included. And this is the iteration control, and this is the basic settings, atom and their Cartesian coordinate point. So then you can select this SCF input, right click, run option to run this job. Here you can see, suppose if you want to run this job on parallel, suppose 5 core, 10 core, 15 core. So there is no limitation of core, you can define up to 128 core. Then you can click on this run option to run this job. In the bottom of the page you can see this is the job manager where the SCF input is in the running condition, and in the meantime you can go to the simulator, select this NanoDCAL, then you can select this analysis. Here you can see this is the analysis parameter. So you can select what parameter you want to calculate. So I would like to select this effective mass, and in the first cell you can see this is for the holes and electrons. The -1 is for the valence and -2 is for the second valence band, and 1 is for the conduction band and 2 is for the second conduction band, and this is 1 is for the spin up and 2 is for the spin down. And here you can see this is the K-point sampling. Then you can click on this generate file. So similarly you can run this effective mass.input file. And if you want to calculate the complex band structure, so again you can go to the simulator, select this NanoDCAL and go to the analysis, and here you can select this complex band structure. And here you can see this is the space grid number n1, n2, n3, and this is the number of energy point, and this is the energy range. Then you can click on this generate file, and similarly you can run this complex band structure.input file. So you can wait till the calculation finished. Once their calculation finished, their output will be generated. In the job manager you can see all the input calculation has been finished and their output has been generated. Here you can see this is the complex band structure.xml file. Select this complex band structure, right click and click on show view. Here you can see this is the complex band structure. For the effective mass output file you can select this log file, click on open containing folder, and here you can see this is the effective mass.mat file, and this file will open in the MATLAB. So I would like to open my MATLAB. So from browse option you can upload your project folder in the MATLAB. You can see this is my project effective mass, and then you can click on select folder. Here you can see this is the effective mass.mat file. So double click on this effective mass.mat file to load this project, and here you need to write the command data and then press the enter. If you want to show the effective mass output file, so you can write the command and then you can press the enter. And if you want to show the output of mass longitudinal transversal, then you can write the command. So for the mass longitudinal you can write this command and then you can press the enter, and this is the output for this mass longitudinal. And if you want to show for the mass transversal, so again you can write the command and then you can press the enter, and here you can see this is the output for this mass transversal. So thank you for watching the video. So first I would like to import the silicon from my local database. So for this you can select this file option, go to the import option, select this import local, and here you can see this is the material database that exists inside this software, where you can see 0D material, 1D material, 2D material, 3D material, and some organic material is there. So for silicon you can select this 3D material, select this semiconductor, and here you can select this silicon and then you can click on this open. So this is silicon crystal structure that I have imported from my local database. And if you want to make a surface slab, then you can click on this build option, and in the build option you can see multiple options are there. So as per your need you can design the structure. So I would like to select this surface slab, and here you can see this is the Miller indices scale value. So I would like to select 100 and then you can click on this build option. So this is the surface structure of this silicon atoms. Right click on the dashboard and select labels, and then you can click on this supply. So here you can see this is the position of silicon atoms, and then you can click on this convert to crystal option, and here you can change the vacuum energy ABC. Here you can see I have changed the vacuum energy of ABC, and then you can click on this build option. So you can select first silicon atoms, and from property explorer you can change their atomic position XYZ. So again you can select this second silicon atoms and change their atomic position. Again you can select this third silicon atoms and change their atomic position. Again you can select this fourth silicon atoms and change their atomic position. Again you can select this fifth silicon atoms and change their atomic position. So again you can select this sixth silicon atoms and then change their atomic position. Again you can select this seventh silicon atoms and then change their atomic position. So similarly you can select one by one silicon atoms, and from the property explorer you can change their atomic position XYZ. So after changing the atomic position of all atoms, you can click on this recalculate linker bond, so that all atom will be connected by covalent bond. Then again you can click on this build option and then go to the redefine crystal, and here you can redefine the crystal in transport direction, that is C. So I would like to increase 3 times in the direction of C, and then you can click on this preview option, and here you can see the length has been increased, and then you can click on this build option. If you want to delete some undesired atoms, so you can draw the rectangle, select the atoms and then press the delete atom. Then you can click on this hydrogen passivation to passivate this silicon surface structure with hydrogen atoms. And you can draw the rectangle, select this hydrogen atoms and press the delete atom. Again you can click on this convert to crystal option, and here you can increase the vacuum in the direction of C, and here you can see the vacuum has been increased. Then you can click on this build option. If you want to make it centrally fit, so you click on this center option. And for the optimization calculation, you can select this simulator, select this NanoDCAL, go to the relaxation, and here you can see this is the relaxation parameter, where you can see this is the basic setting: electron temperature, cutoff energy, exchange correlation, LDA, GGA. This is the K-point sampling, this is the relaxation method, this is the molecular dynamic, and this is the conjugate gradient. So I would like to select this molecular dynamic, and this is the force convergence criteria. Then you can copy this checkbox, and here you can see this is the iteration control, density matrix, simultaneous matrix, total energy, and this is the basic settings, arrangement by element by atoms, and this is the Howard atoms, and this is the Spintronics application. Suppose if you want to include the spin, collinear spin, general spin, and then you can click on this generate file. So once you click on the generate file, in the project window you can see the relax.input file has been generated. So you can select this file, right click, select this open with, and this is the script for this silicon surface structure, where you can see what parameter we have defined. This is the calculation name, relaxation, and this is the method of this relaxation, MD, molecular dynamic, and this is the force convergence criteria, and this is the basic settings: electron temperature, cutoff energy, exchange correlation, and this is the K-point sampling, and here you can see no spin is included, and this is the iteration control, and this is the atom and their Cartesian coordinate point. You can right click on this relax.input file, select this run option, and if you want to run the job on parallel, suppose 5 core, 10 core, 15 core, so there is no limitation of core, you can define up to 128 core. Then you can click on this run option to run this job. In the bottom of the page you can see the relax.input file is in the running condition, so you can wait until the calculation finished. When this relax.input file calculation will finished, then in project window the atom relax.xyz file will be generated. In the job manager you can see the relax.input file calculation has been finished, and their output atom relax.xyz file has been generated. So you can select this file, right click, select this open with, and this is the optimized silicon structure with their Cartesian coordinate point. So in the calculated log.txt file, you can get the optimization step and maximum atomic force. So you can select this file, right click, select this open with, and here you can see this is the relaxation procedure, and this is the step 0, and this is the maximum atomic force, and this is the step 1, and this is the maximum atomic force. And in the bottom of the page you can see the structure relaxation finished, and this is the time taken by this calculation. And this optimization graph you can plot in MATLAB, Origin, and any third party software. So I would like to open my MATLAB, and from this browse option you can select your folder into the MATLAB. So you can see this is my project. you can select and then you can click on this select folder. Then you can open this crystal folder and here you can see this is the calculator result.met file. So to plot the graph you can click on this new script and here you can write the script for plotting the graph. So this is the script for plotting the graph. You can see this is the step 0 to 16 and this is the atomic force that I have entered the data from the log.txt file. So you can select this run option to run this job and here you can see the graph has plotted. And this is the final optimized graph of silicon surface structure with respect to maximum atomic forces. In the x-axis you can see this is the optimized step. On the y-axis you can see this is the maximum atomic force. So thank you for watching the video.
Hello everyone, in this video I will demonstrate you how to make an interface of different material by CAD to atomic. I click on file option and want to import my material first. So I click on this import and I want to import from local library. So click on import local from my database. I go to this 3D material, semiconductor and type S so that I can reach my silicon material and would like to open it. Now silicon material has been loaded in my database dashboard. Now I want to import the another material. So I click on file option, click on import, import local. Then would like to visit this 3D material, conductor, pure metal. So I want to take one metallic material that is called gold and click on open. Now gold and silicon both material with same lattice has been imported. I want to make an interface. So I click on this file of build option and go to the CAD to atomic. Here I have to draw the rectangle. So I will click on this add rectangle item and click here so that it will add the rectangle. Then I will right click and then again right click and click on set so that I can set the material here in this rectangle. I would like to choose here. So two material I have loaded. I want to choose this material as a gold left material and then click on OK button. Now again I want to add one more rectangle. So click on this add rectangle and click here and hold the left mouse and move the position and then right click on it and click on set the material. Choose the middle material. I want to take silicon and click OK. Now again I want to click on this add rectangle. So three material interface I want to make it and click anywhere. Hold the left mouse then move the position. Then right click and set the material of left material interface, right material interface. So I choose gold here and click OK. Now my three material has been loaded and assigned with these rectangle. You can create more number of rectangle and different material can be connected or interface can be created like that. Click on calculation. Now automatically this window will pop up that will call fill junction with atom. Now I can maximize this window so that I can visualize whole the screen. So I hold the left mouse and move this scroll it so that visualization can be done from here. Now I want to define the length of my material. So this length I want to define 0.5 nanometer of gold, 1.0 of middle silicon material and 0.5 I want to take right side gold electrode. Direction is same for all the material. Now you can see this is a grid size, N and M range, scan angle, rotations and strain. Strain percentage, strain on the first surface, second surface or both the surface. According to your convenient, you can choose. Click on preview so that you can see the preview of a structure before final build. So click on this preview. Once you click on it, the preview can be visualized in this black screen. You can hold the right mouse and move the cursor so that you can visualize the gold and silver semiconductor interface, and click on build option. You can zoom by click on this zoom viewer and hold the left mouse and then move the cursor. And for position rotation of this structure, click on this mouse arrow and you can move it. You can see how the interface between three material can be created. So similarly, if more multiple materials are there, you can follow the same procedure for 5 material interface, 6 material interface, 7 material interface, so that that kind of structure can be created. And for the simulation, you can run the simulation by using either NanoDCAL software or by using rescue software, and you can plot the band structure and density of state and other electronic, optical, electrical, thermal, mechanical properties. For more information, please contact to Impulse Technology. Thank you very much. This is my user interface called Device Studio. Now I will click on the file option, then click on import option. First of all, I would like to import the material from my database. There are two type of option to import the material. One is called import local, that we have one library of material database exist inside this software. And apart from that, second option is called import online. From material project open source library, you can also import a new material. First of all, I would like to import from my local directory. So I click on import local and locate the directory where the software is installed. I would like to locate the 3D material and click on conductor, pure metal, and let's suppose I take gold material. I selected it and click on open file. This is single crystal molecule, single crystal. Now I would like to click on build option and click on redefine options. I want to define as a face centered, conventional cells, and then click on build. Now I would like to make a supercell. I would like to go to the build, redefine the crystals and repeat 2 by 2 with 4 times in C direction. Then click on preview and click on build option. Now I go to this home button and click on X by view position and delete the undesired atom. So I draw the rectangle and press the delete option. Similarly, I can draw the rectangle and click on press delete. Then again go to the home direction and click on ZX view. Now I can select this all atom by drawing the rectangles, uncheck this atom and press delete option. To remove the undesired atom, I can follow the procedure. Now I would like to create the vacuum. I will go to this convert to crystal option to create the vacuum inside this unit cell. So I change this value of AX to 20 and I drag and drop. B value similarly I would like to change to 20 angstrom to create the vacuum in this unit cell. Now vacuum has created. I can click on build. Now I would like to make center So I will click on this center along A to make it center and B as well. So it is in center region along A and B axis. Now I would like to import a molecule. I will go to this import local and click on 0-dimensional material and take alkynethyl molecules. Now it has imported. Now I can click on select all atom. I can draw the rectangle to select all atom and click on mirror. And normal vector I can define in x, y, z position and define the distance. .7105 angstrom and copy this checkbox and click on apply. Now it has been copied, so mirror has created. Now I will go to this convert to crystal. Now I would like to click on convert to crystal and increase the Z dimension vacuum space. Now both crystals are inside the unit cell and click on build. Now I click on this alkynethyl, draw the rectangle, press Ctrl C to copy it and click on this gold atoms and press Ctrl B. Now I draw the rectangle to select it and press center to make it centrally fit. Now you can see it has been joints. The alkynethyl molecules have joints with gold atoms. You can also rotate it. So left and right is a gold materials and middle one that is called alkynethyl molecule. Press home. Now I can click on convert to device. Click on left electrode and right electrode. You can define the left, right, top, bottom, front, back electrode. 6 probe device can be simulated. Click on preview before build. Now vertical lines has been drawn, that is called electrode. Click on build button. Now the device has created. The left and right electrode is there. Now this is how to make the device of 2 terminal using this device studio. If you want to make a 3 terminal device, you can click on this simulator, NanoDCAL and transistors. And this is a transistors where you can define the transistor thickness. You can apply the gate voltage and define the region of gate and define source voltage and click on generate file Now default parameters, all the required input file for this device has been generated.
So first I would like to import the silicon material. So you can click on this file option, select this import, and this software have two options to import the material. Either you can import the material from local database that exists inside this software. So here you can see this is the material database, 0D material, 1D material, 2D material, 3D material, and some organic material is there. Or you can import the material from online database like Material Project, open source database, crystallography. So through API access, it will make the interface and you can directly import. And here you can enter the chemical formula and then you can click on this search option. So I would like to select this silicon and then you can click on this search option. So here you can see this is the silicon with different space group. So I would like to select this silicon and then you can click on this add option. So this is the silicon atoms that I have imported from my online database. And if you want to simulate this silicon, so you can click on this simulator, select this NanoDCAL and go to the self-consistent field calculation. And this is the SCF calculation where you can see this is the basic setting, electron temperature, cutoff energy, exchange correlation, LDA, GGA, and this is the K-point sampling. This is the iteration control, density matrix, Hamilton matrix, total energy, and this is the basic settings, arrangement by element by atoms, and this is the Howard atom where you can see SPDF combination is there. And this is the Spintronics application. Suppose if you want to include the collinear spin, general spin, so as per your need you can define the parameter and then you can click on this generate file. So once you click on the generate file in the project window, you can see the scf.input file has been generated. So you can select this file, right click, select this open with, and here you can see this is the script for this silicon atoms. And this is the basic settings, electron temperature, cutoff energy, exchange correlation, this is the K-point sampling, and here you can see no spin is included, and this is the iteration control, this is the silicon atom and their Cartesian coordinate point. So you can select this file, right click, select this run option. If you want to run the job on parallel, suppose 5 core, 10 core, 15 core, so there is no limitation of core, you can define up to 128 core. So you can click on this run option to run this job. In the bottom of the page you can see this is the job manager where the scf.input file is in the running condition. So in the meantime you can select this simulator, go to the NanoDCAL, select this analysis, and this is the analysis parameter. So as per your need you can define the parameter. So I would like to select this Hessian, and here you can see the value of delta, and again I would like to select this Phonon band structure. So here you can see this is the Phonon band structure and this is the symmetric, and this is the Brillouin zone path related to this silicon atoms. Then you can click on this generate file. So similarly you can run this Hessian.input file, right click, select this run option to run this job. Again you can select this Phonon band structure.input file, right click, select this run option to run this job. And in the job manager you can see all the input calculation is in the queue condition. Like when the SCF input for this silicon will finish, then Hessian calculation will start automatically. So you can wait till the calculation finished. So for the thermoelectric property you can wait till the Hessian input will finished. So here you can see the Hessian input calculation has been finished, and then you can go to the simulator, select this NanoDCAL, go to the analysis, and here you can select this ZT, and here you need to import the object file of the silicon. So here you can click, and here you can see this is my project. So you can open this file, and here you can see this is the silicon, and then you can click on this NanoDCAL crystal file, and then you need to select this file, and then you can click on this open. And here you can see this is the K-point sampling, this is the Q-point sampling, this is the energy range, maximum energy, minimum energy, and this is the interval, and this is the temperature range, and this is the direction. And if you want to calculate the Phonon density of state, so this is the Phonon density of state, you can select this file, and then you can click on this generate file. So in the same way you can run this ZT.input file, right click, select this run option to run this job, and then again you can select this Phonon density of state.input file, right click, select this run option to run this job, and you can wait till all the calculation will finished. In the job manager you can see all the calculation has been finished and their output has been generated. So this is the Phonon band structure.xml file. So you can select this file, right click, select this show view, And this is the Phonon 1D structure for this silicon material. And if you want to export your raw data, so here you can see this is the export option. And here you can define the format like JPG, PNG, BMP, PDF, text format. So any format you can select, and then you can click on this save option so that you can easily export your raw data in any format. And this is the thermoelectric property.xml file. So you can select this file, right click, select this show view. And this is the conductance with respect to temperature. And in the plot type you can see multiple options are there, like this is the Seebeck coefficient, this is the Seebeck coefficient with respect to temperature, and this is the thermal conductivity with respect to temperature, and this is the thermal conductivity with respect to temperature, and this is the ZT with respect to temperature. And if you want to show with respect to chemical potential energy, so this is the ZT with respect to chemical potential energy. So you can select any plot type, like this is the conductance with respect to chemical potential energy. So in the same way you can select and you can show their output data. And this is the Phonon density of state. So you can select this file, right click, click on this show view, and this is the Phonon density of state with respect to energy.